All right, we'll start out with any questions. All right, so we last left off. We had just derived the formula for moment of inertia. Sum of all the little m's and r squareds. In other words, we take an object, we break it up into a whole bunch of pieces, and the key thing that I want you to pull out of this is the fact that the distance has more of an impact than the mass does, because this is squared. And we can demonstrate that relatively simply. I have a meter stick here, and I'm just going to put a 200-gram mass on it. The meter stick's about 100 grams-ish. So it's basically 300 grams I'm holding up. What is the weight of a 300-gram mass? Or how would you find it?
Kilograms times gravity?
The spirit of what you're saying is right.
Or mass times gravity, I guess.
Wait, say it again.
Mass times gravity?
Closer. You can just leave her hanging there. What's the formula you're doing?
The weight. Force of weight?
All right, so weight equals,
mg.
yep. All right, so M, mass. What is G?
Gravitational.
Gravity,
Force of
9.8.
gravity.
All right, I heard three different voices at once.
Force of gravity.
Oh, no, weight is the force due to gravity. What is G?
9.8.
All right, near the surface of the Earth in SI units.
Acceleration.
There we go. Acceleration. All right, so 300 grams, which is about this 0.3 kilograms, times 9.8 meters per second squared. And doing the fancy math here, we end up with 2.94 newtons. All right, so I'm holding up 2.94 newtons, eventually. And there's a certain amount of strain. I can definitely feel it in my hand as the edge of the meter stick's digging into it, so let's move my hand over just a little bit. And it takes a certain amount to hold that up. But if I move my hand closer to that end of the meter stick, does it get easier or harder? I'm still holding up the same amount of weight.
Will it get easier?
You're not sure?
Easier.
Easier.
All right, you spoke with more confidence.
Sorry. I said easier also.
Yes, but yours more that went up at the end. Why? It is indeed a whole lot easier to hold it like this than to hold it like this, even though I'm holding the same amount of weight.
Because when the lever arm be long, it's easier to go to.
You were on the right track there.
Yeah, I want to be. It depends on the lever arm.
Yes?
So when it's long, it's easier to go in circle.
Okay, it's easier for this to go in circles? Is that what you said?
I forget the concept.
All right, so help Naveen out. I heard some other voices. Oh,
Yeah. So, we go far away from center of the mass.
all right, so we do have a longer lever arm. This is the natural pivot point here,
Yeah.
because this is where I'm holding it. So we do have a longer lever arm.
It's not even, the weight is not even both sides, which makes it harder to hold from that end versus the end closer to the mass?
If that were the case, make sure I understand you. If I put another 200 gram mass at this end, how would it compare my holding it here with a 200 gram mass there versus holding it here? Let's find out. Let's start over. Let's go back to where it originally was. I'm going to, I started down this path because of something I think I heard Manal say. I'm going to skip over that at the moment, and you can bring it back up if you wish. It's also quite possible that I just misunderstood what you said. All right, so sort of forget some of that stuff that I was saying. Not that it was inherently wrong, it was just not what I wanted to do. All right, we're going to put this thing at both ends. And think about how much effort it takes to swing this thing back and forth. And now I want to set up something similar with the exact same weight. All right, so these are roughly have the same weight. And they're not exact, but roughly the same weight. So think about the amount of effort it takes to rotate this back and forth versus to rotate this one back and forth. No. There we go. Now, there's not a lot of mass here, so perhaps we can adjust that to add more mass. But which one is easier to rotate back and forth? Given the two situations.
The second one.
All right. Now, once I get them going, which one's easier to stop?
The bottom one?
Yeah. So very similar to the more mass it is, the harder it is to accelerate. The more moment of inertia there is, the harder it is to accelerate, which means speed up or slow down or change directions. So if I take an object to roll down a ramp, and this one is solid, and I have another one that's hollow, let's make them the same mass. So I have more mass farther away, and don't forget that that distance has a bigger impact. This one will have more moment of inertia. Which one's going to be easier to get rolling? And I think we actually have these. Let's see if I can find these props. It is one of those days. All right, I guess we won't do that. All right, so I have two objects here. This one has a same mass, same radius. Just this one is solid, a solid disk, and this one is more of a donut. Which one has a greater moment of inertia?
The second one.
What?
This one.
You pointing at that one? Or this one?
This.
I'm not sure which way your finger is pointing. Are you pointing at this one?
Yeah. Yeah.
So I asked which one has a greater moment of inertia? Well, let's think about that. Since it's related to the mass, which is the same for both, and then how far away that mass is from the center, which one has more mass farther away from the center? Yeah, all the mass is some distance away. This one has a bunch of mass that is right there at the center. So this one does have a greater moment of inertia. I bigger. So this has a greater moment of inertia. Which one is easier to get to roll? Which one can we turn more easily?
The solid one.
Since rolling requires turning, which one's going to roll faster?
The solid one.
So that one should be able to make it down the hill faster. Looking at it from a slightly different point of view, energy. They both have the same mass, they both start out with the same amount of energy. It's all gravitational potential energy to start with, mgh. Same mass, same acceleration of gravity, same height, same amount of energy to start with. As it rolls, this potential energy changes into kinetic. Well, we have two types that we deal with here. We have the 1/2 mv squared. Sorry, I didn't give you a chance. 1/2 mv squared, which is the energy related with how fast that thing is going down the ramp. Plus 1/2 I omega squared, which is how the energy it takes to get it rotating. If the moment of inertia is bigger here, that means more energy is spent on getting it to rotate, which means there's less left over to get it to actually move down the ramp. So with a bigger moment of inertia, again, more energy goes into rotational kinetic energy, less energy into linear kinetic energy. And this is the thing that is how fast it's going down the ramp. So the one that is less hollowed out should win in the races. Now there's one other bit that if this is a perfect roll, there's no slipping at all. It turns out that the mass and radius really are not that critical, that the mass, so if ideal roll, the mass and the radius are irrelevant. However irrelevant is spelled. Never quite sure about that letter. And what it really comes down to is that fraction up front. Because the moment of inertia of a disk, 1/2 mr squared. The moment of inertia of a hoop is mr squared. And I'm not sure I can get him more smart right now. The moment of inertia of a solid ball is 2/5 mr squared. The moment of inertia of a hollow ball, or we'll just call it shell, spherical shell, 2/3 mr squared. What really matters in terms of how fast it's going to go down is this fraction up front. If I raced a disc, a hoop, a solid ball, and a spherical shell, this would get down the fastest. Followed by the disc, then the spherical shell, then the hoop. Now, why the mass and the radius don't matter is really beyond the scope of this course. If you really want to know, I can zip through an example really quickly after class if you want to stick around for that. And despite a couple of false starts there, we got to where I wanted to be. So questions?
This is kind of random, but what's the difference between the capital R and the lowercase r? Like, do they mean different things?
Oh. In the context of moment of inertia, the lowercase r is the distance to a specific bit of mass. So if I wanted to find the moment of inertia of this system right here, if I treat this as my mass, then little r is the distance from here to here, and over here, distance from there to there. Or I could look like this tiny little piece of the meter stick, and little r would be the distance from here to that tiny little piece of the meter stick. When you see the little r, big R combination, this is the overall radius of the stick. And usually in that context, that's supposed to be a capital M, because that's the overall mass. So instead of thinking of it as a whole bunch of little parts, those would be the values for the whole thing. Other questions?
I'm still a little confused about that.
About the big R, little r, or?
Yeah. Like, wouldn't R be the same? Or are you talking about like R from like this point where you're starting? That's R. Like lowercase r.
Lowercase r is, when we derived, sorry, that was the first an incomplete sentence, so let's try a couple more. When we first were deriving moment of inertia, and I started with kinetic energy, and the question I asked was, what is the speed, since kinetic energy is 1/2 mv squared, what is the speed of an object that's not traveling all at the same speed? So if I take this meter stick here, and I just start rotating it back and forth, well, the point out here is traveling much faster than a point down here. So the speed of the stick is not a constant value. Because this travels, in the same amount of time, they go through the same angle, but this travels much farther because it's farther away. So the way that we dealt with that is to find V, we actually have to think of this meter stick as a whole bunch of tiny pieces. So little r is the distance to each of the tiny pieces, and you would add them up.
Oh, okay, now I get it.
Okay. But in the case of this, if the big R would represent, would be, the whole length. Well, in the case of a stick, usually they use capital L for that, for length. Because why use the same letter when you start using different letters? Right, other questions up to here? All right, let's throw some stuff. And I say let's, that sounds like we're all going to throw stuff. You get to throw stuff on Friday, but well, hopefully not throw stuff. What I'm going to do is I'm going to take this right here, and I'm going to swing it around my head. I'm going to do it from over there. So I'm going to swing it around my head, and I want to hit something with it. So I'm going to be standing somewhere in this space right here, swing it around my head, and I want to hit a spot on the board. I want to hit as close to that spot as possible. So let's just do an overhead view of the classroom. I'm going to be standing somewhere around here, and I want to hit that spot. I'm going to swing this thing around in a circle, going that direction. At what point do I let go of the string so that I can hit that spot? Now, in order to describe where I let go, think of this as 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. And I can handle ones and twos. If somebody says 6:45 and someone else says 6:46, that's fine, but I really can't differentiate between those when I actually let go. sort of good at the half-hour mark, but. So where would I release it in order to hit the spot?
I would say around 3 o'clock.
Right there? Anyone else?
I was gonna say 2.
And by the way, I've never hit a student doing this. This was the exercise. Did I tell you about the I did not hit Scott bit? When I was teaching middle school, I was doing this routine, and I did get closer to Scott than I intended. But I did not hit Scott. That was first period. Last period of the day, some students come in and say, "Hey, Dr. Fox, I heard you hit Scott this morning." No, I did not hit Scott. I have not hit anyone. The most damage is I damaged a periodic table once. All right, anyone else? We have a guess at 3 o'clock or speculation at 3 o'clock and 2 o'clock? It's okay to stand up and go, "What were you thinking?" It's obviously, and then give me another number. All right, then we will go with those. Make sure the string is looking pretty solid there. I don't think I'm going to hit you, but you are sort of close. Depends on how much faith you have in me.
Not
She
that I
has
don't
less
have
faith.
faith, but.
All right, so first, I want to line up with the X there, and 3 o'clock would be release it at this point right here. The whole point of the other story is I haven't hit a student yet. All right, so I'm gonna release it when it gets here. Now I need to do it slowly enough so I have some control. So force of gravity will have an effect, but 3, 2, 1, go. Just a little bit too early, but. Now we're gonna do 2 o'clock, so. But you got a little bit more faith, I guess, or not, we'll find out. So that's 3 o'clock, 2 o'clock is about right here. Three, 2, 1, go. A little bit too far there. But it's somewhere in between those two that I just did. The lesson is, when I let go, what is the path going to be?
It'll be tangent to the point that you let go.
I assume that's what your hand gesture was. So it should have been, like drawing, hard to believe, not perfect. It should be going in a straight line. Newton's first law of motion, an object, different language. An object's going to keep doing whatever it was doing unless it's acted on by some outside force. So once I let go, what is the outside force acting on it?
Gravity?
Yeah, so that's why it's not a line drive as soon as I let go, it does fall some. But since that is acting up and down, there should be nothing affecting it left and right, so as soon as I let go, the thing should be traveling in a straight line. So if something is traveling in a circle, what conclusion can we draw?
It's gonna keep going in a circle?
So why did it not keep going in a circle when I let go?
Well, you were holding on to it,
And then I let go.
yes. So would this have to do with the force of tension?
Something to do with force of tension. What is the force of tension doing?
It's pulling away from you, basically.
Ooh.
Or,
Which force of tension are you talking about? Because we did, if that's me and the bob there, and I have a string connecting it. So there's me, bob, string. There is a force. There are lots of tension forces there. So which one are you talking about?
between you and the string.
This one right here, or that one right here? The one acting on me or the one acting on the string?
On the string, I would say?
The one acting on the string is pulling towards me. Is towards me.
Oh, okay. It would be the one acting on the string towards the bob.
That one right there.
Yeah.
That's the one that you were talking about.
Yes.
Going away.
It's gonna go.
Okay. Now, ultimately, we care about the bob traveling in a circle. Which way is that force acting? What force is causing the bob to travel in a circle? Some of this is a repeat, so if you feel like it's already been answered, feel free to say it again. All right, so let's drop back to, when I let go of the string, did the bob still go in a circle? All right.
Tension force? Tension force?
Yes. Tension was causing that bob to travel in a circle. As Manal had indicated earlier. What I'm getting towards is that if something is not traveling in a straight line, there has to be some net force acting on it. So if somebody is traveling in a circle here, there must be something causing that. And that force is pulling it in, because the bob wants to go this way, but something just keeps pulling it back in towards the circle. How many of you have seen Godfather 3? One, okay, one of you. There's a line from Pacino. Every time I try to get out, they just pull me right back in. That's what's going on here. It's trying to go in a straight line, but something just keeps pulling it back in. In this case, it is tension. But there is a generic name that we have for this type of force. It is not the one that is usually given. This is not a new force. This is just the name we have for that force which pulls an object towards the center, which causes it to travel in a circle. Pretty sure it's from the Latin. This is center, century. And PET, seeking. It is that force pointing towards the center of a circle. We have, obviously center and centra look close enough, but PET, we actually do have words in English with that root meaning seeking. Just throw it out there. What word do we have in English which has PET in it that means seeking?
Move toward the center. Move toward the center. Toward the center.
It's moving towards the center.
Yeah.
I was looking for a word that had PET in it, though. It's sort of disguised. I'm going to go ahead and spoil this one. The other one I'll give you more time on. But PET, competition. Yeah, or compete. You're seeking out, basically, an opposing side. Now, there is that other word that is commonly used here. I will talk about it, and then potentially not talk about it again. And I'm not I have heard the claim that it doesn't really exist. It's sometimes listed under the false force or the illusion of a force. However, there is a proper way to use it. It's just that most people don't. And so let's talk about that one. The centrifugal force, or centrifugal force, depending upon your upbringing. And then there's centripetal or centripetal. Centripetal flows much better for me. If I say centripetal, that is an acceptable pronunciation, but that's mainly when I do it is to emphasize it is this one instead of that one. Because in a hurry, they sound alike, centripetal, centrifugal. Obviously, center. And fleeing. What word do we have in English has this F-U-G in it that means fleeing or something similar? Yes. There's also a relatively famous expression, tempus fugit, which means time flies. Now, the reason where this actually would apply is if we think about the forces acting on that bob, it is being pulled towards the center. This is the bob or stopper, I guess I was using here. And then we have the rope here, so the rope's being pulled like that, and then pulled here. The forces that are pointing away from the center, this force is technically a centrifugal force. This one technically is a centrifugal force. Those are not the forces keeping the bob or the stopper traveling in a circle. This one right here, the one that we care about. This is a centripetal force. Centrifugal or centrifugal force also shows up in the rotating reference system. So we generally think of, I was sitting still, and the bob was going around me when I was swinging it. But if I looked at it from the bob's point of view, it felt like he was being thrown outwards, but he wasn't. So that's why sometimes it's labeled as a false force, because it seems like he's being thrown outwards. So in the rotating reference system, centrifugal can also show up. And there's a cartoon in the hallway over there where I believe the hero was about to be sliced in half by a laser, and that comes up. All right, so it's just easier if we never use that word again. So far we have dealt with, well, actually, let's, for just a second, what is acceleration? The formula?
Change of velocity over change of time.
And up till now, at least mathematically, all the change in velocities we have dealt with dealt with change in speed, speed up or slow down. But now we are dealing with a change in direction. So this exists if speed up, slow down, and that's chapter 3, or change direction. And that's chapter 8. I'm pretty sure it's chapter 8. It's in this next section. There's, of course, a formula. Centripetal acceleration. So if we're dealing with acceleration based purely on change in direction, that's equal to v squared over r. Sort of think about that. You're driving a car and you're taking a turn. If you're driving 50 miles an hour or 20 miles per hour and taking a curve, which one's easier? So the faster you're going, the harder it is, because the faster you're going, the greater the acceleration, which means the greater force is needed to keep you in that curve. You're driving at 20 miles per hour taking a curve. You can take a curve like that, or you can take a really sharp curve. Same speed, which one's easier? Because R is bigger. This is known as the radius of curvature. In the case of my swinging the stopper around, it's just basically the radius of that circle. In the case of a curve where you're going along fine, and then you do a curve, and then you go along straight again. Radius of curvature, as you imagine, there's a circle here. And it's the radius of that circle which would cover that part of the curve. Questions to hear? All right, so you're driving along, you're going around a curve, flat road. What is the centripetal force keeping your car from going off the side of the road? So, we've got a curve here. You're driving along. Your car wants to do that because things want to travel in a straight line. What is the force that keeps your car from going in a straight line?
Inertia.
Inertia?
Yeah.
No, inertia, two things. Parts of nitpick. Inertia is not a force. And the other one is conceptually, inertia is the property of an object that makes it want to travel in a straight line. And I'm asking what's keeping it from traveling in a straight line? What's preventing it from traveling in a straight line? Specifically, what force is preventing it from traveling in a straight line?
Centripetal force?
Well, this is not a new force. It's going to be one of the forces we've already dealt with.
Oh.
One of those. And it's not other.
Normal force.
Normal force is acting perpendicular. So normal force is not going to, remember that the force has to be towards the center. Centripetal force is towards the center of the circle, and normal force is this way. Give my overhead drawing here. So not normal.
Yeah.
Direction?
Direction.
Yes.
Yeah.
If you've ever driven on ice, you know that it's very hard driving on ice to take a curve. It is friction that is acting towards the center of the circle. Any of you play corners growing up? You and a sibling in the seat of the car, and as the parent took the curve, you would lean way too much into your sibling? If it was your younger sibling, shame on you. If it's your older sibling, well done. You were not being thrown out. You were not being thrown outwards. Again, back to the same thing. If you're in the car, you're here in the seat, you want to be traveling in that direction, but that car is preventing you because the car turns. Yes, you're going to get closer to the outer part of the car, but that's because the car is stopping you from, the car is going to exert some force on you, or your sibling, or the seat belt, or the friction between you and the seat. There are lots of different forces in the car that are keeping you pulled inwards. You just want to go this way. You're not trying to go, as you go around a curve, you're not going in that direction. You want to, again, you want to go straight, the car is cutting you off. If you're wearing a seatbelt, the seatbelt will do a lot of that work. guess it depends on which side of the car you're on. Sorry, flashback to my youth. Yeah, I'm trying to think, I probably didn't wear a seat. We had to wear a seatbelt in the front seat, but other than that, it was fair game. So the centripetal force usually was the door, the sibling, or the front seat as you hold on to it as.
So, this is a stupid random question about that.
Okay?
Like, if there's a fly in the car, why does it not just go towards the back if you're moving?
I'm assuming it's making adjustments as it goes. It's the same thing if I had a cup of coffee going around a curve, or a drink going around a curve, I can adjust so that it doesn't go splattering up against the wall. Also, the air inside the car is moving along with it, so it's not like as you go around a curve that the air is leaking out one side and then coming in the other side. You know, you're not developing a breeze usually. So that would be my explanation for the fly. Probably if you did really sophisticated studies, I suspect the density of air inside the car gets slightly denser on one side than the other. But I suspect you would really need the $1 million equipment to measure that difference. I guess it depends on how fast you're going and how sharp a curve it is. So let's take a look at the problem. This is a side view, that's a table. And I'm gonna put a little hole in the middle of the table, so this is side view. And then overhead view. There's a hole in the middle. I'm gonna have an object here. Really, you can find a different color. I have an object here that is attached to a string, and this object is going to travel in a circle. That string, so think of the object there, that string goes through the hole and is attached to another mass down here. So I'm going to call this mass 1, this is mass 1, and this is mass 2. I am not worried about the fact that the string here is at a slight tilt. I'm just going to treat it like the string is straight across and then down. Now when I do this, I'm going to get mass 1, I'm going to get it swinging to move around, and I want mass 2 not to move at all. So mass 2 in static equilibrium mass 1 definitely not in equilibrium because it's changing directions, but it's traveling at a constant speed. So let's make the distance from here to here 0.5 meters. So, something like that. Somewhere there. And let's say it takes 3 seconds to go around once. I'm going to change that slightly. Let's say it takes 30 seconds to go around 10 times, or 10 revolutions. Connect it slightly better to the lab you're going to do on Friday. And what I want to know is, what is mass 2? I guess I do need to give you mass 1. We'll make this 0.1 kilograms. So what does mass 2 have to be in order for this to work? I am going to put one other simplification in here. No friction. The tabletop is frictionless. So we start out with the typical force diagram. We have mass 2 hanging down below, mass 2. And we've got that rope, and then we have mass 1 here. There's a table, but I really don't care about the table. What I really care about are just these two masses. So what are the forces acting on, just give me a force in the object and direction.
Tension,
Okay? Acting which way on what?
acting on the rope, towards M1, and from M1 to the rope.
On M1?
On.
Yep.
And then on the rope to mass 2,
That's what you're saying?
yes,
Okay.
and then on mass 2 to the rope.
Okay. Tension, done. There's no other. We assume mass 1 is already going when we come into the problem.
There is a weight force between M2.
You said weight?
Weight, yes.
Okay. Acting which way?
Go down.
Okay.
And the M1 go down also.
Now, if we were doing the full force diagram, we would have the other parts of those pairs acting on the ground, acting up, but we're not concerned about those for this problem. So weight is done. Also assuming an ideal rope.
There is
Normal acting which way on what?
From the table up to the, from the, oh, well, the table's not there. So, from the mast down to the table?
So normal force is pulling the mass 1 down.
Oh, it's going the other way, sorry.
All right, so we have the normal force acting there. And then there's one acting down on the table.
Right.
There's one other normal force pair, which really does not impact our problem here, but we've gone this far with what I have. There's one more normal force. Not on mass 2.
And the other
there
way.
is
Yeah. There's gotta be a reason the rope is bent like that. So there is a normal force here. It's called Y sub R. All right, so I've got my two masses here that I care about. It's gonna be dark enough. All right, so this is an equilibrium. What does that tell you about these two forces if this is an equilibrium?
Their magnitudes are equal.
Yes. So we're going to plug in that F equals ma. So for mass 2, I know the forces up minus the forces down is equal to 0. In other words, the tension equals equal to the weight. And what's the formula for weight? That's mass 2g. Again, we're trying to find mass 2, so it better show up somewhere. All right, so over here, vertically, is mass 1 in equilibrium vertically?
Yes,
Why? Why do you say so?
the normal force and the weight acting opposite.
They are, but I can give you an example where weight and normal force are acting opposite, but it's not equilibrium. Okay, so physically, why you are right, it is an equilibrium. They do balance each other out. How do we know they balance each other out in this problem? If they are not balanced, in other words, if it's not in equilibrium vertically, what would the mass do?
It would be falling
Or,
or rising.
yeah. Yeah, this thing's traveling in a circle, in a horizontal circle. It's not grinding into the table and it's not suddenly lifting off the table. So, yeah, they're balanced. And so for mass 1, that's a 1, I know that y1 minus w1 is equal to 0, or, as was said earlier, the normal force is equal to weight of 1, which is m1g. Now in this direction, this tension, is it in equilibrium horizontally? How do you know?
There's no opposite force.
All right, that's definitely a huge indication of it. What is the other clue that was given in the problem to tell us that it's not in equilibrium horizontally? Something that actually relates to this chapter. Yeah, the direction is constantly changing. Velocity, therefore velocity changes, therefore there's acceleration, therefore not equilibrium. All right, so we have the tension is equal to mass 1 times the acceleration. And I'm going to put a little c next to the acceleration just to indicate this is centripetal acceleration. It is traveling in a circle, the acceleration is centripetal. So my tension is equal to mass 1 times my acceleration, which is v squared over r. So we now have enough so we can figure out what the tension has to be in order for this to travel in a circle. So mass 1 is 0.1 kilograms. The radius, 0.5 meters. The speed, what is the speed of this? This definitely comes into play. That would be the time for what? Yeah. So the time it takes to have one revolution is called, so the time for technically one cycle, that's a 1 there, one cycle of repetitive motion. Is called the period. The symbol used for period is a capital T. This is the reason I don't use capital T for tension, because capital T are reserved for period. So the period is 3 seconds. So now we know the time it takes to go around. How do we find the speed? What is the formula for speed?
0.1 per 3.1 kilogram per divided by 3.
But what are we dividing by 3?
Yeah.
I missed.
Kilogram.
Oh, that divided by 3?
Yeah.
No, not for speed.
Can't remember if it's distance over or distance divided by time.
Either one. So it's distance divided by time or distance over time, depends on if you want to express it like math or the way it's written. So what is the distance that this thing is traveling? traveling in a circle. A little more than 6 radians. But what's the formula? There's 2 circle formulas. It's going to be one of those 2.
2 pi r?
That's the one.
Okay.
So it's traveling along a circle, so this is the circumference. So that's 2 pi times the radius divided by the period. So that's 2 pi times 0.5 meters divided by our period of 3 seconds. So it ends up being 2 point something. Actually, if someone would be kind enough to give us an actual number here.
.09?
09.
No. Yeah. Oh, no, I did it wrong, I'm sorry.
Is it 1.05?
2.09.
Someone else got 2.09? What am I doing wrong in my head?
I got 1.05.
It's.
Those would cancel out there, that, so it should be 1 point.
Are you in radians or degree mode?
That's one of the different.
That shouldn't make a
It
well,
is, I think it does. Cause you're using
Oh,
pi.
no, I got
2 different.
so the 2 and the 0.5 should cancel out. So then you're left with pi here, so that's 3.14159 something, divided by 3. 3 goes into 3 once.
1.05.
Yeah, 1.05, all right. That makes more sense. 1.05 meters per second squared. So we end up with 0.2. Oh, 1? Or point, no, 0.21. Units? Not seconds.
Kilograms?
What do we find? What is this 0.21? Yeah, somebody just said it. It's tension. We just found the tension. We found the centripetal force, the force that's required to move this thing around. So we know what the tension is. It's the same tension at top and bottom. So M times G, so M2G equals the tension. M2 times 9.8 is equal to 0.21. So M2 is 0.21 divided by 9.8. Divided by 9.8 each side. .023. Someone's gonna correct me.
I just got 0.02.
0.02. Seems like there should be a 0.02 something. If we're dividing by 10, it'd be 0.021. We're dividing by something a little bit less than that, so I figured. 1.4, okay. Units? Not Newton. Or Newton meters, is what the other thing I heard.
Is it just kilograms?
It is just kilograms. So mass 2 needs to be 0.0214 kilograms, in other words, 21.4 grams. That would be enough.
Did you use F equals MA for that last equation? but just
For
solved it.
this one right here, we did F equals MA to find the tension, but from here, I knew that the tension and the weight had the same magnitude. So technically, yes, I used F equals MA, but A was 0 for this. So the process was the tension minus the weight of 2 is equal to 0. The tension therefore is equal to the weight, which is equal to M2G. And so that's what I used. So in the lab, you're gonna have a stopper here that you're gonna swing around. You do not want the tape touching the bottom of the tube, because if the tape touches the bottom of the tube, then you are introducing additional forces. You want to swing this stopper as horizontally as possible. Now, you're not going to be holding the string here. You're going to be applying masses to the bottom down here and swinging the stopper around so that this mass here does not move, ideally. You're going to time how long it takes this thing to go around. So you'll know the distance from here to here, in essence that. You will time 10 or 20, I can't remember what I have for the 110 lab, but I think it's 20 revolutions. And you'll time how long that takes. So you'll get the period. If you know the radius of the curve, the radius of the circle, and you know the period, you can find how fast it's going. You are eventually, you'll know the tension because you'll know the hanging mass. That's one place where this is different from what the lab is. In the lab, you know what M2 is. You don't have to calculate it. In the lab, you're going to pretend you don't know what M1 is. You'll eventually do a plot of V squared versus tension. It'll be beautiful. And from that, you will find an experimental mass 1. That is the lab. Now, one thing we are not taking into account in 110 is the fact that as this thing spins around, notice that the rope is sagging. That it is not out like this, like I did in that example, it is down like this. It turns out that if you do a plot of V squared versus tension, it actually makes 2 changes to the official, if we actually went through it more hardcore using trig. It makes 2 accommodations which cancel each other out, and so you actually still, this is just as legitimate as what I do for 151 and 251. They take into account the sag. I'm not asking you to, but you still get the same answer as it turns out. And I think that we will talk about gravitation next, and on Monday, and I think we'll get to black holes. Figure out how big does the sun need to be in order to create a black hole? How big does the Earth need to be in order to create a black hole?